Okay, picking up where we left off, we're talking about how ATM was essentially designed to handle all sorts of traffic. Voice traffic, data, everything. And they were right to think, why should we have, data circuits and then voice circuits running side by side? Let's take this whole multiplexing concept and let's make it a little bigger, and let's just build a network that's capable of handling everything. Now, long distance voice, the most important feature in a network environment for voice is latency. In other words, I can't have, where I ask grandma a question and there's like a pause. And then they answer. I mean, it's got to be rather quick. So they wanted to keep the latency down. So what they did is they built ATM with an incredibly small packet size. It's 48 bytes, not kilobytes, bytes. Tiny, tiny, tiny little packets. And it was designed so that it could go through hardware kind of in fixed length, and the sizes, unlike TCP/IP where the sizes could be small and large. These guys were fixed size, headers, and it could be read by hardware to make it go a little bit faster. Very little software intervention to make it go. Anyway, bottom line is the ATM was a bunch faster, about 1.5 meg to up to about 620 something megabytes. So it was a heck of a lot faster, and you could aggregate these guys together. You could just grab a couple of ATMs and bolt them on, and make a bigger ATM and a bigger ATM and a bigger ATM. And again, this was money-making idea. At this time, what they were thinking is voice is king. Of course, that tells you when this occurred. Voice is king, and therefore higher dollar value associated with voice. And if I tweak and optimize my network for latency, I can charge more for that. So I'm charging by quality of service. For example, here's an email that's coming through, and we know it doesn't matter how long it takes for that to arrive. If it was delayed by 10 seconds getting across the nation, no one would ever care. But if I said hello grandma and it took 10 seconds for it to arrive at grandma, yeah, I think we would notice. And so they were actually able to charge more based upon latency. They could say, well, this class of service gets this much and this class of service gets this much. Because remember, back then, they were all, publicly traded companies trying to make money off of voice, and this data stuff was just kind of a running fad, and maybe it would go away one day. Ha 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 ha. Okay. So traffic quality was kind of sort of invented. The whole concept of traffic quality first showed up in ATM. The next thing I'm going to talk about is what's called these high density multiplexing techniques. The first one is time division multiplexing on page 337. So let's say I want to take a waveform and I want to break it up into itty bitty slots for, the first, as an example. The first second belongs to customer A, and the second belongs to customer B, and the third second belongs to customer C. So if I'm going to do that, my waveform is better be extremely high frequency in order to be able to cut these things up into pieces and have no one notice. Clearly, there's no network that has the granularity of 1 second. That was just an example. So because I want to have lots of time slots, the frequency really, really has to be high, and therefore we're talking light, not electrical impulses anymore. So these are most all of these high density multiplexing techniques are doing over fiber optic cable. Okay, so one more time. Why does high density multiplexing need fiber optic cable? Because the frequencies have to be really, 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 really high. Okay, good. So the first one they talked about was synchronous optical network, SONET. So SONET was a setup where they could get some amazing data rates out of these guys. Okay, here's megabits, here's gigabits. Yeah, 34 gigabits per second transfer. Yeah, big stuff. So, and again, you could bundle these things together. You could take, and this was, by the way, and this was designed so that, even multiples, right? You could have 4 incoming OC3s going to an OC12, and then 2 OC12s going into an OC48. See how they're done with doubling or tripling as they go up the scale. And so, consider like a web where things just kind of converge and then keep going. Anyway, that's how it was all designed. So the only weird part about Sonnet is, unlike the other types where we were talking about, frame relay and X.25 and ATM, Sonnet really, 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 really is an L1. It really is, down at the physical layer, because it's now specifying a completely different type of connection, going from electrical impulses on a wire to light impulses on a cable. So that's time division. The other one, of course, is frequency division. In the same way, if I'm going to have frequencies and I'm going to be breaking them up, I kind of sort of need that frequency to be pretty doggone high. So typically what they do, they on page 337, they talk about the 3 different bands. They have like a high, medium, and low light band, different frequencies of light being sent down the cable. Kind of cool. And then of that, they have 3 frequency bands, and inside each frequency band is 50 time division channels. Each one of those channels are somewhere around 10 gigabits each. Wow. So the combination of both the frequency and time division is how you end up getting these monstrously huge data transfers. Okay, so just to make things crazier than they already are, there's a statement in the book that I'm going to have to read to you because it's kind of cool. It talks about each FDM channel, frequency division, may support a sonnet, and each one of the sonnets could have multiple ATMs. So, yes, I could have, some sort of a frequency guy going on, and maybe it comes up to an OC 192. So I could be running sonnets through this thing, and then each one of the sonnets could have multiple ATM channels. I could have one heck of a lot of conversations over this cable. That's some cool stuff. Okay. So, the next thing we're going to talk about on page 338 is how all this fits into the TCP IP stack. So, I just mentioned that the fiber people are kind of different, so clearly we're talking about an L1 kind of scenario there. But even with the L1 thing, kind of underpinning the choice of connectivity there, WANs are basically considered sort of like a long distance LAN. Okay, so a WAN from a stack perspective. Clearly they are not using Ethernet, because Ethernet has some very strict requirements for, cable length and signal attenuation and, broadcast and can you hear me and, all that stuff. So it's not Ethernet running over these cables. It's different types of, so it takes an L2 change. So even if, this is the point, even if the cable looked the same as an Ethernet cable, it ain't an Ethernet cable. It may physically look like one, but I am not running Ethernet over that cable. So I could have the same L1 cable, Ethernet coming in one thing, and it looks like a Category 5 cable coming out going over here, but it is not Ethernet. So don't call these things Ethernet cables, because you could be talking Ethernet or you could be talking something else. So these WAN cables, are different. Okay, so we're all talking about L2. Now, whenever I make a conversion between types of cable, like an L1 cable or an L2 signaling kind of a thing, whenever that occurs, then it takes a router to make that happen. So routers are the ones who basically take it up to a higher level, figure out like the size differences, because, for example, I'm sending you an Ethernet frame at 1,500 bytes, and you want to go to an ATM frame. Well, I'm going to have to, at that layer 3, I'm going to have to take that and fragment that, break that up into pieces, and put it in ATM and send it on. So only L3 does that. L3 is the only place where I can change the size of my packets. Incoming packet coming in here and outgoing packet going there. L3 is the only place where that takes place. Okay, so, IP is where all this happens. And typically, this happens inside a router. The routers are the ones who do this for a living. You can buy specialized IP devices that are not routers, but that's not what we're talking about. Essentially, whenever we talk L3, we're talking routers. So, I'll say it, although it's not technically correct. In order for me to go from Ethernet to X.25, or Ethernet to frame relay, or Ethernet to ATM, or Ethernet to SONET, it's going to go through a router. Okay, cool. All right, we have reached the end of this chapter, and we'll see you guys again in some future chapter.